So in this video, we're going to talk about the fourth type of conic, the hyperbola. You can see the definition is the set of points in a plane such that the difference of distances between two fixed points, the foci, is constant. So very similar definition to the ellipse, except for the word difference in there, which is going to make remembering the equation pretty easy. We're going to have an equation that looks pretty similar to the ellipse, except instead of having a plus, we're going to have a minus. So this is the equation for the hyperbola, and the center is going to be the point HK, and this one too will have a secondary formula that we'll get to here in just a minute. Now, the hyperbola, again being a conic, you've got a cone and you've got a plane intersecting it. Well, in the case of a hyperbola, the plane will intersect somehow like this, where there's going to be two distinct parts of the shape. You can see there in the middle we'd have a gap. So the two different types of hyperbolas that we're going to study would be the ones that open up sideways with the two distinct parts, or the type that open up and down with, again, the two distinct parts. The foci will be inside the individual parts, kind of like that. And we'll also have major and minor axes identified in a similar way. So down here, the major axis would be the X, because the foci lie on that horizontal axis. And we would say the minor axis then was the Y. Over here, our major axis would be the Y, and our minor would be the X. So the foci in that picture lie on a vertical axis, so we have a major axis of Y. Okay, so when it comes to putting the picture together and labeling everything, we'll go ahead and start with our standard form equation. We're going to be centered at 0, 0 in this case. And unlike the ellipse, the hyperbola is going to be recognized by a major and minor axis on the positive term. So whatever term is positive, that's going to be the major axis. It's not going to have the size effect of A and B anymore, but the first term being positive, that's always going to be the major axis. So I'm going to go ahead and construct my picture here similarly, where my center is going to be 0, 0, and I'll have this hyperbola opening to the right and to the left, doing something like this. All right, so that's the hyperbola, and I'm going to backtrack a little bit only because this is how we're going to get the graph put together, but just so you're familiar with what it looks like and why we have a major axis the way we do, you can see how the hyperbola would lie. You can see the foci being here and here, and all of the other details as well. But again, I'm going to backtrack a little, and before I actually want to construct that, I'm going to end up putting together a rectangle. Now, the rectangle that we're going to put together is going to be centered at our center, and the endpoints of the rectangle are going to be where the A's and the B's come in. So we know the major axis is X. You saw the graph in there just a moment ago. This guy would be A0, and this guy would be negative A0. We'd have a 0B, and we'd have a 0 negative B. So again, by me labeling them the way I did, I've suggested that A is always associated with the major axis, and therefore A is the distance from the center to the outside of the box along the major axis. B is the distance from the center to the outside of the box along the minor axis. Again, B and the minor axis go hand in hand. Now, the reason why this box is so necessary before constructing the graph of the hyperbola is because you're actually going to have asymptotes that kind of shield in or box in that graph. So the asymptotes are going to run through each corner of the box and the center. So those asymptotes, again, those are going to bound our graph where that needs to be. So now coming back, I'll go ahead and sketch in the hyperbola a little more accurately than my first picture. And you can see, once we figure out the A and the B, we can put the box together. Once we have the box, we put the asymptotes in. Once we have the asymptotes, then we're actually able to sketch a pretty decent graph of that hyperbola. The C value for the foci would be the same as well. So C0 and negative C0. And then when it comes to the definition that you saw how similar it was to the ellipse a few minutes ago. And so the definition is going to work the same way, but instead of having the sum of distances, we're going to have the difference of distances. So in the last section, we said D1 plus D2 equal 2A. Well, now it's not going to be a plus. Instead, it's going to be D1 minus D2 is going to equal 2A. And so the picture is very similar. I don't want to mark it up too much on the video. It's going to be pretty ugly if I did. But by definition, that is what the hyperbola is doing. Now, as far as the secondary formula goes, we have another little triangle in here. There's our triangle we're going to focus in on. And you can see this would be an A. This would be a B, and then if I take this hypotenuse right here and I pull it down, needing to be the longest side of the triangle, as I pull it down, it's actually going to be the same length as C. So our secondary formula now would be A squared plus B squared equals C squared for the hyperbola. So you'll want to go back up to the box above and fill that in as the secondary formula for the hyperbola. All right, so in the first example we look at, we're just going to graph this hyperbola, and you'll see kind of how I showed you in the last part, how we're going to start with that box. Now, the information that we're going to be looking for is over on the right of your screen. We're already in standard form, so we can already identify the center. Do be a little bit careful here, though. We've got the y first minus the x, which not only does that imply that the major axis would be y, but we want to gather the coordinates for the center correctly. So the center would be 1, 2. It's a pretty common mistake to flip-flop those on accident, so be careful. The center is going to be 1, 2. As I just mentioned, since the y term is positive, that's the major axis, therefore the minor has to be the x. Okay, now because y is major, the number underneath here, that's your a squared, which means that a would equal 2. That would be the minor axis, which means this is b squared, and b would equal 3. So I'll start construction of the graph, and our center is going to be at 1, positive 2, and from the center we're going to move 2 units up and down. So 1, 2, and then 1, 2 puts us back here on the x-axis. From the center we're going to move 3 units right and left. So right there, and 1, 2, 3 puts us right there. Those 4 points now are going to allow us to construct the box. And once you have the box constructed, now you can throw the asymptotes in through each corner and the center. And because the major axis is y, we know that this thing's going to open up and down. Kind of like that. The asymptotes are bounding it in there, acting like magnets. And so there's a pretty detailed sketch so far of what we have. Now we would still need to look at the foci. And our secondary formula for that would be the a squared plus b squared equals c squared. So 4 plus a 9 equals c squared, and c equals the square root of 13. So the square root of 13 is approximately 3 something. And so you could see that from the center, if we counted up and down approximately 3 something, it does put us outside of the box. And that's something you'd want to double check. If you happen to use the wrong formula, the one for the ellipse is very similar. If you happen to use the wrong formula, it puts you inside the box, which we know is incorrect. So it's a great way to check. So the foci would have x coordinates of 1. And the y-coordinate would be 2 plus or minus the square root of 13. So we move up a distance of square root of 13 and down a distance of square root of 13 when your y is starting at 2. Okay? So the last thing then that we'll need to do would be look at the equations of the asymptotes. These are linear, so anytime you need the equation of a line, you need 2 things. You need a point and you need a slope. Now, conveniently, the slope here can be found a couple different ways. You can obviously look at the graph, look at your points, and however you need to run a formula, or you can look back at the original and see that because of these numbers and how that box was constructed, we rose 2 units for every 3 units we ran. So rise over run, change of y over change of x would be the 2 over 3. You have a positively sloped line and a negatively sloped line. So we have a plus or minus. And then we'd also need a point. And it makes sense to use the point 1, 2 as a point because it's common to both lines. So the first one would be y minus 2 equals 2/3 x minus 1. And the second one would be y minus 2 equals a negative 2/3 x minus 1. And so we'll clean those up, and I think we'll have it finished. So there we have y minus 2, 2/3 x minus 2/3, y equals 2/3 x plus 2 minus 2/3. I just moved the 2 to the other side. That way it's a little easier to do the fraction subtraction. So that's going to be a plus 4/3. And then over here, similarly, negative 2/3 x plus 2/3. Negative 2/3 x plus 2/2 gives us a negative 2/3 x plus 8/3. So those are the equations of the asymptotes that we're looking for. I'm not going to copy them down again. They come right up here. But that's the information we're looking for when we graph a hyperbola. All right, in the next example then, we're going to come up with the equation of the hyperbola given asymptotes at plus or minus 4x and intercepts at plus or minus 3, 0. So if we're going to come up with the equation of hyperbola, I've got that written down, which tells us that we need the center, HK, and we also need A and B. So I'll go ahead and sketch an approximate picture to what I have. I know that my intercepts here at 3 and negative 3 tell me that my graph is going to do one of these. And I also know that I have asymptotes at plus or minus 4x. Now, before I sketch those in, remember the earlier picture. If you have these 2 parts, there's a box sitting in the middle of them. So I would do your best just to sketch a rough box in there. And then the asymptotes that we're speaking about would be these right through here. This would be y equals 4x, and this would be y equals negative 4x at that point. So I think from the picture it's pretty clear that we have a center at 0, 0. And now it's a matter of finding A and B. A is the distance from the center to the outside of the box along the major axis. And by looking at the picture, the A value would have to be the 3. To find B, we're going to be a little bit clever. B would be this guy right here. But if you look carefully, that guy is also the same as that guy right there. So what I'm going to do is I'm going to take the x-coordinate of 3, I'm going to move up, and I'm going to see what y-coordinate corresponds with that. Well, I'll go into my asymptote and say that if x is 3, my y is going to be 12. So this guy here That's going to be 12, and that's our b. So our center being at 0, 0, the x-axis being major tells us this is where we are so far. We're going to have a 9 under the x squared, and we're going to have a 144 under the y squared because of the b. So there's the equation of the hyperbola.